Okay.
All right. Good day, everyone. My name is Jacob Anders. I'm the high-performance computing technical lead at the CSIRO. And together with me, I have August Simonelli, product engagement manager at Red Hat, and Erez Cohen, vice president for cloud and artificial intelligence at Mellanox. And today we'll be talking about SuperCloud. First, a couple of words on my organization. CSIRO stands for Commonwealth Scientific and Industrial Research Organization. We are Australia's national science agency. As such, we are a big consumer of scientific computing. We've got significant amount of compute and storage on-prem. And this is a very important topic for us because to lead in science, we need to have leading innovative information technology in order to be able to support our scientists and their workloads. Let's have a brief look at our existing workloads, dominant workloads, I would say. We've got CPU and GPU-based HPC clusters. Those are the classic HPC systems. You can think of them as batch queue. Very homogeneous, single image systems. Well, probably shouldn't say single image because that implies shared memory, but basically we're thinking about a cluster which runs the same image across the entirety of the nodes. Why is this important? We'll touch onto this later. So our current workloads mostly look like what's on the slide. However, what we're seeing more and more as the time goes is we have more users exploring the emerging fields of research, such as cybersecurity, machine learning, bioinformatics. And those workloads typically have very different requirements. While they'll still value performance, it is very important for the users in those domains to have more flexibility and adaptability. Unlike in the batch queue scenario, they would like to have more influence over what their operating environment looks like. Quite often, they would like to bring their own. Hence, the homogeneous approach does not work for them that well, and they are looking more towards heterogeneous, loosely coupled systems. Looking at this worries me a bit because I see a growing disconnect here. I see classic HPC perfecting its own tools, which are very good for this particular domain, but they're difficult to adopt to other domains. At the same time, practitioners of, for example, precision medicine or machine learning tend to develop their own tools. And I see the divergence, and it's not a good thing because if we can develop a single platform to cover the entirety of it, we can work together. We have more opportunity for collaboration, and we can make tools better. And this is how computing became great. Instead of working on single-purpose devices, which we see on the right-hand side of the slide, we joined forces to build general-purpose computers, and that made our lives so much easier and better. So I think it's worthwhile to pursue the same avenue with scientific computing. Instead of taking multiple different directions, consolidate our efforts and go in one consistent direction. So in order to be able to achieve that, we would like to build an HPC system which is more cloud-like, or a cloud that's more HPC-like. We call this vision SuperCloud. SuperCloud is both an architecture and a set of systems that we are building up at the CSIRO. And to finish off this introduction, I would like to point out the main differences between classic HPC and cloud. In my opinion, the big one is the interconnect. In HPC, it's all about maximizing the bandwidth and minimizing the latency. Other features come second. In cloud computing, it's orthogonal. Features such as security, isolation take precedence. Also, the mode of operation is very different. Cloud is all about DevOps, while HPC is still in the batch queue realm, which, again, it's a bit of a disconnect. So in order to be able to build a supercloud, we need to bridge some of those gaps. And when we embarked on this journey, we realized that this is too big of a job to take up on our own. Hence, we joined forces with our friends and partners, leaders in the respective fields. And I would like to take this opportunity to hand over to Erez and talk about the interconnect that makes building superclouds possible.
Thank you, Jacob, and good afternoon, everybody. I'm Erez with Mellanox. Last talk of the week, so thank you for staying so late. I'll talk a little bit about what will be a proper network for SuperCloud. SuperCloud requires a super network. You want to be able to do all those workloads on one single homogeneous system, and you want to make sure that the network, which is the heartbeat of the system, will not fail you down on any of those workloads. So what do we need from such a network? Well, first, we'll have a lot of data. We're in a data-driven world these days, and the data is growing exponentially. We'll need to move that a lot. So we need a very high bandwidth, very high throughput network. the workloads are distributed. They need to run very fast and collaborate together. So we need a very fast network. That translates to low latency. We need a very low latency system. We want the system to be very efficient. We want the network to be not taking too much CPU for doing network services. So we need hardware offload, and it's not just one thing. It's network offloads for transport, for virtualization, storage, and security. There's a lot of different types of hardware offloads that we need. The network needs to be flexible because it is a cloud, and we need it as an SDN. So we are looking for something that is software-defined by nature, and obviously we want standard, open source, off-the-shelf kind of a solution. So those are the requirements that we have from our network, and InfiniBand network fits these requirements very, very well. InfiniBand is an SDN by design network that was designed in about year 2000. It has the highest bandwidth today in the market, running 200 gigabit per second today. It has the lowest latency, sub-microsecond latency between servers. It is designed to be fully hardware offloaded. It is open source and open standard, again, by definition and by implementation. It supports both bare metal virtualization and containerized environment, and it can run both on CPU and GPU computation elements. Even though it is very high-end kind of a solution, it's still designed to be able to run any type of workload. It is not only for HPC kind of workload. So this is the approach we decided to take in the SuperCloud. I'll talk a little bit about InfiniBand. Most of you maybe know InfiniBand from the high-performance computing world. InfiniBand connects the largest supercomputers in the world. This is just an example for the last top 500 supercomputer list, and InfiniBand connects the #1, #2, and #3 largest computers in the world, among many, many others. So more than half of the list is interconnected by InfiniBand. But InfiniBand is definitely not only high-performance computing. We're seeing to the InfiniBand connecting storage system, connecting big data system, and lately a lot of the HPC system is heavily using, the machine learning systems or AI are heavily using InfiniBand. You can see a few examples here, a system from Facebook, Preferred Network, Sony, the NVIDIA Saturn cluster. The one thing that they have in common, all of the system, is a combination of GPUs and a lot of GPUs together with CPUs that create a huge and massive data transfers that only InfiniBand can handle that, and including some advanced features that InfiniBand has, like in-network compute and other things. So InfiniBand is definitely not only HPC, and the scientific world definitely want to use InfiniBand. Let's look at InfiniBand at a glance. I don't think that all of you are familiar with that. So it is a standard that's defined by the IBTA Trade Association. It's a complete 7-layer kind of stack from physical all the way to application. We talked about the bandwidth, 200 gigabit per second. InfiniBand has a very unique transport service called RDMA. Today, RDMA is also available on Ethernet. RDMA is a key for allowing application to utilize the network properly. It has full CPU offload by design, or at least on the Mellanox devices. It has built-in kernel bypass. The guys that understand Ethernet may be using DPDK to do kernel bypass. With InfiniBand, you don't need that. It is by design. This is what brings the low latency. It has remote direct memory access, so we can do read and write over the network, which allows us to build very interesting application in a very different way. While in the past it wasn't very popular, today most of the frameworks in the industry already take advantage of RDMA. InfiniBand is different than Ethernet in some cases. In some cases, they're very similar. But when we take InfiniBand and want to run it inside OpenStack, we need to understand that there are differences. InfiniBand doesn't use MAC or IPs that everybody are familiar with. In Ethernet, instead they're using GUIDs or global identifier and local identifiers addressing mechanism. It uses different network partitioning. It uses partition keys instead of VLANs or VXLAN that are more familiar with Ethernet. It uses verbs API to allow the application to access the network instead of socket. So there are some differences between the different approaches, and what we have done is we basically allowed InfiniBand to be first citizen in OpenStack, and I'll talk a little bit how we did that. But before we do that, let's talk a little bit about the software-defined nature of InfiniBand. So InfiniBand was designed a long time ago as an SDN solution. The SDN of InfiniBand is called SubnetManager. This is the software-defined application that configures. It basically goes and configures all the addressing and the segmentation and quality of service, everything that allows the network to operate properly. Unlike Ethernet, where the SDN layer is working in most cases in a sideband management port, InfiniBand is designed for all the management to run on the same port as the network. So it is called in-band management. We use the same port to actually carry all the management. Allows us to build much more efficient systems with less connectivities, less cables, less ports. At Mellanox, we build an integration layer between InfiniBand SDN and Neutron so that when you orchestrate an OpenStack cloud, Neutron will talk to the OpenStack, to the InfiniBand SDN, and will allow to configure the fabric according to the cloud configuration. A very nice features that we get almost for free is that we can use all the standard and non-standard topologies that InfiniBand provide us. In Ethernet, it is not so much common to have different topologies, but in InfiniBand, we have very advanced topologies that we can build that meets our workloads. Fat trees are, those Klaus trees, hypercubes, toruses, and dragonfly pluses. Those are all advanced topologies that we can get for free with OpenStack with InfiniBand. I mentioned RDMA. RDMA is critical. It's critical for the application to take advantage of the capabilities, and we want to make sure that in a SuperCloud, all the nodes can take advantage of RDMA. That includes bare metal, that includes VMs, and that includes also containers. Bare metals is easy. It's kind of just work by default. For virtual machine and for containers, we're using SRIOV to expose the NIC, or the HCA in the InfiniBand language, directly to the VM or to the container so that it can take advantage of RDMA. And by that, actually, we can get even additional capabilities like other accelerations, GPU direct. I'll mention that in a minute. Containers are relatively new, and we are working on getting RDMA and InfiniBand in general into containers environment. What you can see here is how do we provision RDMA into the containers. Unlike VMs, we do need to use other mechanism to provide the RDMA interfaces into the container. We're using CNIs, the container network interface, and the device plugin of Kubernetes to provision the relevant element into the containers runtime environment. This is work in progress. It is working. You can see a lot of reference designs on how to do that. Very soon, by the end of this year, it will be completely automated and provisioned by Kubernetes and other environments. One of the features that is very important, especially around the machine learning and HPC workload, is GPUs. Mellanox has been working for a long time with NVIDIA to allow much more efficient connectivity between GPUs and the network. In the past, you can see in the top right-hand side, it was very complicated to get data from the GPU memory to the network and vice versa. There's a lot of copies. And today, and this is the bottom left side, we have enabled a much more streamlined approach where the NIC and the GPU talk together and allows to save a lot of those copies and reduce latency. And some of you may know that Mellanox were also acquired by NVIDIA, so it's interesting. The last, I think, slide is Ironic. So Ironic is a big deal for OpenStack, obviously. And we've invested quite a lot to get Ironic to support InfiniBand. And not only that, we actually support multi-tenancy over InfiniBand in integration with the InfiniBand SDN. So this is available today. My last slide is just kind of a summary. InfiniBand and OpenStack can work together, even though OpenStack does not know anything about InfiniBand. Everything is happening under the hood in a transparent manner, but allows us to run a complete InfiniBand stack with OpenStack today. With that, August.
Thanks.
Thank you.
All right. So for us at Red Hat, where this all started was when, back in Australia, because that's where Jacob and I are from, or where we live anyway, we started to have a discussion about this. I've known Jacob for years, and he comes to me and he says, I'm at CSIRO, and I'm doing something kind of fun. It's kind of interesting. It's HPC, and I'm like, OpenStack, HPC, okay. And he says, look, I'm using things like RDO, I'm using things like PackStack, and we're thinking, this is tough. He says to me, the technical efficiency is low. I'm using too many tools for the job, as he was suggesting to you before. I'm bouncing all over. Do you think there's a way that Red Hat could support a convergence of something like HPC and standard cloud? And he said that statement to me, we want to make HPC more cloud-like, and I kind of thought, well, it sounds a bit buzzy, but we want to make everything more cloud-like. So I think maybe we have something there. Now, as you see this week at the summit, the community is very aware of bringing together these worlds, of bringing together bare metal, of bringing together virtualization. Ironic is everywhere. It's even in this room. It's there, but it's very hard for someone who's trying to build this up with a small team to actually do it with support. So we decided if we could work together, perhaps we could optimize the best of all these worlds, but at a commercial level as well, of course, as an upstream level. So what we want to do at Red Hat is act as an extension of the CSIRO team. So we let them innovate, but we also become their voice in the community. We do it in two ways. The more traditional way is the downstream area where we provide like reference architectures, the training. But what we did with these guys is we also allowed them direct access to product management. So when Jacob would hit an issue and wanted to discuss it, not just at a community level, but at a, can this actually be productized, or would this be unsupportable? He can speak through me, with them directly, whatever, to our product managers of the OpenStack product. And this is sort of an untraditional way of working, but it allows that voice to be heard. But it also allows the product managers to speak back to him and say, hey, look, we see where you're going, but what if we did this? Then, of course, there's the upstream support version, which is something we're fairly well known for, but it's something worth calling out. We have plenty of engineers working in these spaces, so we can interact with them for Jacob, for CSIRO. We can amplify that voice. We can just bring them into the conversation. Because we need to bring it back to this main question, right? I love his graphic here, where he's got these old sort of disparate tools, and we want to bring them together. We know the community wants to do it, but there's so much out there. It's a wonderful problem to have. It's a really good problem to have. But it's also one that a smaller team can't solve. So we figured we work together, we would find ways to do it. But how does that look when we're actually working together? It's pretty simple, actually. So Jacob starts off with an idea, or his team starts off with an idea, and they start talking to the community. They grab bits and pieces, they hack it, they make changes, they hash things out. We fail a lot, we succeed a lot, but we get to a solution. We engage the engineers that we need to in the community and have them in the discussion informally. And so we come to a conclusion about how something can be done. He then goes the official route, and this is slightly different to what a lot of the open source and the HPC stuff is used to. He now can raise a ticket with OpenStack, with Red Hat, which will then turn into a ticket that can be worked by our internal teams, can engage our engineers on a formal basis, but not by surprising them, but just by bringing what we've already discussed with them into what could be a productized version. That works through with high-level visibility, and away we go. Eventually, that then works back upstream to raise the right bugs, the right changes, the right specs, or whatever is necessary. And we know that it started in this brainstorming session, has gone through this internal process, has gone right up to the community, but because we started inside and with the internal process, we've been able to know that it will show up as a productized feature. The main areas that we covered to do with this are with integration and certification, bare metal again, and with automation and lifecycle. These were the three major parts where we're working at this point. So to quickly go through them, for the integration guidance and the certification, essentially what we do is we've got all this wonderful tech from Mellanox, and it takes a bit to integrate it into OpenStack. So with OOO and our various technologies, we provide a framework that they can build against to go ahead and integrate into it. And then we can use the same processes that we were using before where we're speaking to product management, we're speaking to community, and then hopefully we can go ahead and get certification for these things. We can get them in tree, so they're upstream, whatever is necessary. And then the other two pieces. The one that's more interesting is Ironic. There is a lot of change required for what he's trying to do, and we're going to show you in just a second. So we've been able to work very closely with the PTL for Ironic. For anyone in the community who needs to participate in that, we're able to use that process and feed it back in. And then the last piece is with our deployment mechanism. So this week we've heard a lot about deploying OpenStack, and it's very exciting, very important. A lot of fun, a lot of pain at times, but it's also something that he just didn't need to be worried about. So he was able to go with OOO, or our downstream version director, and just know that he's going to get specific things, the correct control plane, best practice for integration. He knows he can go to Mellanox or any other vendor and say, look, I'm using this, can you just follow these guides and make this work? And by doing that, we allow him to spend the time to build the really neat stuff, not to listen to this, which I think is the boring stuff. And with that, let's hear that neat stuff.
Thank you, August. All right, let's spend some time looking at the mechanics of the SuperCloud and move on to some of the example workloads. So just to reiterate what SuperCloud is, essentially it's a bare metal OpenStack system with software-defined networking based on InfiniBand. The advantage of taking such an approach is delivering the performance of bare metal, as there is no shim layer that could induce performance overheads, while retaining flexibility of cloud. Because our bare metal is provisioned through the OpenStack endpoints, we have all the bells and whistles that OpenStack typically provides to its users. Because of the SDN capability, we can retain the advantages of isolation and multi-tenancy, which are very important for workloads such as cybersecurity or, for example, precision medicine, while we're working with sensitive data. So essentially, we can support a wide variety of workloads without making any sacrifices. We also came up with quite an interesting architecture, and I find it quite elegant. You might think what you like, but we think it's very neat and lightweight. As August mentioned, we use OOO to deploy the control plane. I'll touch on that a little bit more later. But the distinct part is every component that's not, strictly speaking, required for the OpenStack to bootstrap, we move it to user space. So for example, our Nova Compute exists as bare metal instance in the overcloud. So it's essentially a workload like any other. It's just connected back to the control plane, which not every user is allowed to do. We take similar approach to storage that's provided to tenants. Instead of pre-creating storage, which is typically the case for OpenStack deployments that I'm familiar with, we also make storage a workload. This way we can take advantage of the convenient provisioning model that OpenStack provides and have certain degree of elasticity. So if we need to make changes to storage, scale it up, down, for example, split it and use different storage platforms, we also are able to do that. And essentially, we're building upon the technology that we've presented a year ago in Vancouver with a couple of tweaks, which I'll describe in the following slides. If you're interested in the mechanics of it, I would like to refer you to the Vancouver slides. I thought I will spend the time demonstrating the functionality as opposed to reiterating the previous message. One of the key changes that we've made is as we're transitioning towards production stage of the first SuperCloud-based system, we added high availability to the control plane. We built that using built-in OOO features. So we didn't have to do anything extra. Basically, that came to us for free with a wide variety of features that OOO has. More importantly, we've implemented InfiniBand connected containers to be able to come up with a more lightweight abstraction to run user workloads while retaining the performance that bare metal cloud can deliver. And essentially, this brings us to the point where we can leverage infrastructure as code methodology, but on bare metal. So we can do all the convenient and efficient things we used to do on virtualized clouds without sacrificing performance to the virtualization layer. This takes entire systems and moves them up the stack, making them cloud-native applications. For example, Slurm can be a good cloud-native application in this framework. I'll demonstrate this in a second. And the last thing that I wanted to highlight is with this paradigm, we essentially make infrastructure layer something that's underneath the workload that we don't really have to worry about. It's a bit like assembly. It's down the stack, it's taken care of, but the consumer or the developer doesn't really have to worry about it. And I believe this is something very powerful. All right, so let's have a look at some samples, what SuperCloud can do for us. The first example that I've prepared is a deployment of Slurm using Elastic Cluster. We'll be deploying onto bare metal. Elastic Cluster is a tool developed by University of Zurich. It can be used for a variety of Elastic workloads. It's not just limited to Slurm, but this is what we've been using it quite successfully in virtual machines. So given it's talking to OpenStack endpoints, transitioning from VM to bare metal is as simple as changing the flavor to something that points to our bare metal nodes. There are a couple of other small tweaks that we might touch on later if time permits, but essentially the Elastic Cluster deployment is very portable. Installation is very straightforward, as simple as doing a git clone and putting in some config that points Elastic Cluster to the SuperCloud system, and then defining the workload that we would like to run. And let's have a look what a deployment like this would look like. First of all, we're checking the state of the cluster. There'll be a couple of other instances there, but no Slurm yet. We hop onto the Elastic Cluster node, which has the code, activate the virtual environment that Elastic Cluster is going to use, and we kick off the deployment. What this will do is it will talk to the OpenStack APIs to instantiate the compute resources required. And when that's done, it will SSH into the instances and set up the software that we've requested it to configure. In the interest of time, I'll be skipping through the video so we can spend more time looking at other demos as well. First, Ansible is walking through the prerequisites that Slurm needs to be able to work. The key component is setting up the head node, which is happening just now. And after the deployment completes, we can see that there are additional nodes in server list. Let's SSH into the environment and submit a simple job to verify if the scheduling functionality works correctly. You can see that there are 2 nodes active and ready to accept jobs. Just came up with the simplest possible job to demonstrate the scheduling functionality, just submitting it into the queue and testing the results, which match what we expected. So that's one end of the spectrum, the workload that's, I would say, the closest to classic HPC from the collection of workloads that we were experimenting with to date. From the opposite side of the spectrum come the ephemeral hypervisors. As I mentioned in the previous slides, we do not have any primary virtualization capability on SuperCloud. Our main focus is optimizing performance, hence we're bare metal by default. However, there are some workloads that are not yet containerized and are not able to take advantage of having an entire compute node to themselves. And I think having a virtualization option there, at least in the transition period as we move towards containers, is a good thing. Also, with Mellanox technology, we can have virtualized InfiniBand inside those instances. So while they won't be as performant as bare metals, they can get quite close in terms of the network performance. So my second demo will illustrate deploying a software-defined hypervisor with a very similar methodology to what we use to deploy Elastic Cluster. I used a different system for this demo, so you won't see the instances that we created previously. Here we use Ansible to first pre-create the ports to ensure that we have predictable networking, which is very useful for the configuration later. And as soon as that is done, we move on to create the bare metal nodes. This takes a while, and I'll touch on that a bit more later. As soon as the instances become reachable, we commence the configuration step. I'll skip forward a little bit in the interest of time. We fetch the configuration from the controller deployment to make sure that things will never get out of sync. So basically, we take the controller Nova configuration, apply a couple of changes that need to be made in order to make VNC and such things to work. And from there, we're able to add the nodes to the sales service and initially start running virtual machines, which I'll demonstrate in a second. So after the deployment concludes, you can see that there are a couple more nodes showing up in the service list in Nova. We need to do some sales magic to make them available. And after that's done, we can start running virtual machines on those newly created nodes. So here we've got a simple script that's pre-creating SRO vports and then instantiating VMs with those SRO vports attached. All right, we can see one is already built and one is still building. When that completes, we'll associate a floating IP to one of the instances just to make sure that the connectivity to the VMs and the new hypervisors works as expected. All right, so our ephemeral hypervisors are alive and well. Going back to the slides, let's move on to the final demo that we prepared. The main mission of SuperCloud will eventually be running containerized high-performance workloads. And I think a great demonstration of this would be a workflow that was written by my CSIRO colleagues, Dr. Dennis Bauer from CSIRO Health and Biosecurity, and Piotr Schul from Data61. This is based on VariantSpark, which is a machine learning library which they use for genomic data analysis. And similarly to previous examples, we can use Ansible to programmatically create an environment to run this application and make it available to our users. With this demo, unfortunately, I haven't zoomed in the font as much as I should have, so I apologize if it's hard to read. For that reason, I will skip through the instance creation part because we've seen this twice already, so it's not that interesting. So what happened is the playbook that we run created a baremetal instance, after which it deployed a container to that instance. And inside the container, we've got the VariantSpark workload that compares a specific genomic sample to a reference dataset to identify any interesting patterns and differences between those two samples. Given that we aren't able to see the Ansible, we can briefly walk through the Ansible that's created the container. Essentially, everything that the user needs to be mindful of is defined in this simple file, which defines the specifics of the environment, such as flavor, the number of instances, and so on. In terms of the code that we use to instantiate the environment, we use Ansible modules. With Ansible, transitioning between VMs and bare metals is pretty much transparent. Most likely, the interesting part is here. So those are the Ansible calls that instantiate the container inside the freshly booted bare metal. So now that we looked into the design details of SuperCloud and looked at some of the workloads that SuperCloud can run for us, let's think about the bigger picture. How does this system fit into our scientific computing environments and thinking? I think this slide provides a pretty good summary. After we run all the playbooks, this is what the system state will be like. In addition to the Elastic Cluster VM, which was pre-existing when we ran the first playbook, we've got the Slurm cluster. Here I scaled it up, so we've got 4 worker nodes instead of 2. In addition to that, we've got a couple of the hypervisors, which we can identify by looking at the networks. They're connected back to the internal API network that the controllers reside in. And lastly, we've got the VariantSpark container running in another bare metal instance. So this demonstrates that this disconnect that I was talking about in the opening can be bridged by applying technology like SuperCloud. We are now able to run all of those quite diverse workloads on one platform without having to maintain and update multiple concurrent platforms. Given we've got a few more minutes, I just wanted to reinforce the performance benefits of taking this approach. Those are benchmarks that we run on some of our older hardware. We're about to receive the latest Cascade Lakes with HDR, and we'll rerun those benchmarks, which will be more interesting. But essentially, we see about 20% performance hit on the Limpac CPU performance. In terms of the SRO InfiniBand, bandwidth is pretty much on par with bare metal, which is excellent work on behalf of Mellanox. Thank you, Erez. And there is a bit of a hit on the latency as well. Importantly, we see an order of magnitude of a difference in terms of standard deviation. And this environment was set up without CPU pinning and other NFV-grade features, so possibly this can be further improved. But generally, VMs will never have latency as predictable as bare metal, in my view. So taking the bare metal approach frees us from this burden and enables us to support MPI applications much more comprehensively. So where from here? Essentially, SuperCloud can deliver the task of bridging high-performance computing and cloud. And this provides us with greater flexibility to cater for wider array of workloads, which traditionally wouldn't essentially fit on high-performance computing system. The key message here, I think, is bringing infrastructure as code to bare metal. This is something that's really important. All of the flexible methodology that we develop working with cloud computing systems can now be applied to bare metal. And this leads us to a point where we can start talking about building an API-driven data center, where all we have is a pool of hardware with differential capabilities that we can then use to build software-defined systems and morph them into different shapes as the requirements change, come and go. In terms of the future work, there are a couple of items left on our to-do list. The main thing for me is improving the bare metal boot times. There were some really interesting discussions about that in the Ironic talk earlier today. I'm sure this will continue in the PDG, but I would like to see a scenario where we can create bare metal instances almost as quickly as VMs. And with some tweaks in Ironic, this might be possible. And the key area of focus for us is to make sure that customizations that we made are fed back upstream, so there is less and less burden on us to maintain the solution. And with this, I would like to thank you for your attention and open the floor to questions. Thank you. Blair.
Do you have any concerns about security giving users root access on your bare metal hosts?
Our user base is mainly internal, and we have pretty strong provisions in the CSIRO code of conduct to prevent people from doing bad things. However, this is a valid concern. This is more of a private cloud scenario, so it's less of a concern, but it's still a concern. My main worry here would be people fiddling around with hardware more than they should be for whatever reason. We're thinking about applying mechanisms that will prevent people from changing BIOS settings or reflashing the firmware, things like that. So that'll be the first step. But a valid concern, less applicable to our scenario, but nonetheless, it's something that we'll be looking into.
Maybe I'll add to that. So when the environment is more or less safe, then the answer is holding. When you're looking at more of a public cloud and bare metal, then you may need to add additional capabilities around securing yourself. And then you can look at SmartNICs that have a different CPU runs in front of the server that can run an isolated kind of protection on the server. So we're basically isolating the bare metal from the network and controlling the bare metal through an out-of-band management system. This can be done with the Bluefield, the Mellanox SmartNIC. We haven't deployed that here, but it is doable, and there are public clouds that are doing the same technique.
Any other questions? Go ahead.
Is this kind of discussed in the community somewhere, like scientific working group or something?
I do not believe so. However, I'll be around for the PTG, and I've got a couple of action items I would like to share with the community. So we're just starting this process right now. Plus, there is all the great work that August is doing to advocate for our needs within the Red Hat community as well as upstream. So I haven't done much of this advocating myself, but August, do you have any further comments?
No, I mean, we're continuing to work with the upstream community to make sure it gets there, but we're waiting.
That's right, yeah.
We're waiting patiently.
But happy to talk more at the PTG if you're attending. Thank you. Go ahead. Yes? Not with this presentation.
Maybe repeat the question. I don't think they
Yep.
heard.
The question was about an example of provisioning storage in the same elastic fashion. We do not have a demo on us right now, but there are existing playbooks that implement BGFS that I believe would just work with this system as they stand, maybe with minor modifications. So it's a solved problem. Just given the time constraints, we thought that those 3 workloads would be the best suited. Thank you. So the bare metal part is non-different than a typical supercomputer. In terms of the virtualized part, if we run the elastic hypervisors, those graphs illustrated. So in terms of bandwidth, we're looking good. In terms of latency, there is a bit of a hit, and performance is more variable. However, if an MPI user approached me and asked for resources in a supercloud, they would go straight to bare metal. So they would be running at the 100% performance. Yes, those systems are living in isolated islands. However, as we progress, we hope to onboard more and more workloads onto the supercloud, so we do not need that physical isolation. But all of this experimentation is happening away from our main CPU and GPU systems. I think we ran out of time, so thank you very much.
Thank you, guys.
Okay.